There exists many different probability distributions, some of which we're already familiar with, like the normal and Bernoulli distribution. We've also learned that the normal distribution is the most commonly used distribution. But apart from the normal distribution, today's lesson will introduce the binomial and Poisson distributions. The varying distributions serve different objectives, and this lesson will help us become better acquainted with those still unknown to us. A warm welcome back to Shaw Academy, and thank you for choosing to study with us. Einstein said, "It's not that I'm so smart, it's just that I stay with problems longer." Remember that education is not always easy, and you will experience some challenges during your journey. But the important thing is to keep on going, even when you're faced with challenges. My name is Nina Smith, and I'm the one behind the voice you're hearing now. Remember at the beginning of Module 1, I said we would touch base about your goals. Well, let's talk about them beyond Module 1 and possible memberships at Shaw Academy. Remember that here at Shaw, our vision is to make the ability to gain new skills very accessible at a much lower cost. You've already gained so much, and we touched on Module 2, 3, and 4 so much during this module. But I would just like to remind you that if you take out a membership, you can not only finish this course, but access any of the courses across any of the facilities, which is an absolute bargain. It is vital in this day and age to keep upskilling yourself, whether it is for personal or professional gain. The skills you will learn in this course will not only affect your ability to be a better analyst, but also have the potential to positively impact the future of the company you're analyzing data for. This is your professional diploma course in statistical analysis, lesson 6, where we will be discussing more about sampling distributions. Today's lesson is a jam-packed lesson that'll form part of the building blocks to your analytical career. We will kick the lesson off by understanding the concepts of skewness and kurtosis we discussed in the previous lesson in more detail. Thereafter, we will introduce a few more distributions, not as popular as the normal distribution, but nevertheless important to know of, and we will end the lesson becoming more acquainted with sampling distributions that will eventually lead us to generalized results of the study from the sample to the population. So let's not waste any time and continue this path of self-improvement we're on by better understanding skewness and kurtosis. Let's quickly refresh our memory of what we learned in our previous lesson. We learned that the normal distribution is the most commonly used distribution, represented by a bell-shaped curve. It is also referred to as the Gaussian distribution. The normal distribution is symmetric around the mean, meaning that 50% of the distribution falls to the left of the mean, and 50% of the distribution falls to the right of the distribution. The mean and median are equal to each other when the distribution is normal. The distribution is used to represent continuous data. Therefore, it can take on any value from positive to negative infinity. The normal distribution is said to be uncovered by the French mathematician Abraham de Moivre in 1733. Then a few years later, Pierre-Simon Laplace and Carl Friedrich Gauss manifested the mathematical principles for the distribution, hence why the distribution is also referred to as the Gaussian distribution. We also discussed that the normal distribution can be fully described through the mean and standard deviation. The mean is symbolized by the Greek symbol mu, and the standard deviation by the Greek symbol sigma. The normal distribution is a probability distribution. Therefore, if we sum the area under the curve, then it should result in a total probability of 1. Lastly, we learned that the empirical formula or rule says that when a random variable is normally distributed, 68.27% of data lies within one standard deviation of the mean. 95.45% of data lies within 2 standard deviations of the mean. And 99.73% of data lies within 3 standard deviations of the mean. The normal probability distribution can be represented by the following formula, where E represents the exponent of the natural logarithm. As we've mentioned previously, mu represents the mean of the distribution of x, and sigma represents the standard deviation of the distribution of x. As much as symmetry around the mean might form the perfect bell-shaped curve, real-life data is rarely perfect. Location, variability, skewness, and kurtosis are all measures that tell us more about the data set. In other words, they help us characterize the data set. We already know that measures of central tendency has to do with data clustering around a certain point, and variability tells us more about the spread around the central value. Skewness tells us more about the asymmetry of the distribution, and kurtosis tells us more about the peakedness of the data. So how do we know if the distribution is skewed or not? As mentioned, skewness tells us more about the asymmetry of the distribution and will be present when the mean, median, and mode are not equal to each other. The skewness for the normal distributions is 0, because in the normal distribution, the mean, median, and mode are equal. So if the normal distribution is symmetric around the mean, a frequency distribution will represent with tails as mirror images of each other. If a cluster of observations present on one side of the mean, we describe the data as skewed. In other words, when the left and right side of the distribution are shaped dissimilarly, the distribution is skewed. A distribution can be skewed to the left or the right. If the distribution is skewed to the left, then the data points will accumulate on the right side of the distribution, and the tail to the left will be longer. It almost seems as if the curve is leaning towards the right, so a left skew distribution displays as a right-leaning curve. We also refer to this as a negatively skewed distribution. A left skew distribution has a mean smaller than the median and median smaller than the mode. Alternatively, if the distribution is skewed to the right, the contraction of data points will be on the left side of the distribution and the tail will be longer to the right. The curve will appear to lean towards the left. And we also refer to this as a positively skewed distribution. In a right skew distribution, the mean is bigger than the median, and the median is bigger than the mode. Kurtosis tells us more about the peak of the distribution. Kurtosis is a measure we can use to check if the distribution is normally distributed and provides us with information about the distribution along the tails. Kurtosis also helps us to explain more about the shape of the probability distribution. It also tells us if there are any extreme values in the tails of the distribution. Kurtosis can also be seen as the combined weight of the tails in comparison to the rest of the distribution. As the tails become heavier, kurtosis increases, and as the tails becomes lighter, kurtosis decreases. In other words, if the distribution has a low kurtosis, the data in the tail is less extreme than that of the normal distribution. And if the distribution has a high kurtosis, the data in the tails is more extreme than that of the normal distribution. A normal distribution is said to be mesokurtic with a kurtosis of 3. If the distribution has tails that are heavier or fatter, the peak will be higher and sharper than mesokurtic, and we say that the distribution is leptokurtic. Leptokurtic distributions have kurtosis greater than 3. Leptokurtic has more extreme outliers. So with a leptokurtic distribution, the tails will be fatter and more dense in comparison to that of the normal distribution. Platykurtic distribution occurs when the extreme values are less than that of the normal distribution and when there are less data points along the tails. The kurtosis value is less than that of the normal distribution and might be less than 0. The tails of the platykurtic distribution are thinner than that of the normal distribution. Methods like histograms, skewness, and kurtosis can be used to check for normality, meaning that these methods can help us decide if the distribution is normal or not. As we know, a histogram is useful to visualize the distribution of the data over a continuous interval and provides the frequency of event per value for the data. From the histogram, we can quickly visualize the distribution of a variable. Skewness and kurtosis, like we've just seen, also provides us with more information about the distribution of variables. QQ plots is another method we can use to determine normality. These are plots that divide the range of data into quartiles and plots the theoretical quantiles against the actual quantiles for the variable. We will explore this plot in more detail in later lessons. And lastly, we can also look at the Shapiro-Wilk test to determine if the distribution is normal. This test was specifically designed just for this purpose. Ever heard about the p-value? The Shapiro-Wilk test returns the test statistics, W, and the p-value to us in order to determine normality. But once again, you will have to stay tuned in to later lessons to explore the topic of p-values. Let's pop over to SAS once again, now that we have a better understanding of the concepts of skewness and kurtosis, to investigate how they influence the transformed normal distributions. In the previous lesson, we investigated the skewness of the transformed variable for the wine quality data set. I would like us to have a little bit of a look at another data set, namely the open data sets that is stored as part of SAS Studio. And with those, investigate skewness and kurtosis. So let's go and have a look at those data sets that is built into SAS Studio. So the heart data set SAS allows us to use is free. From this data set, we see that it indicates if a person is alive or if they have passed. Sometimes there is a cause of death, and sometimes there's an age information related to the patient. The data shows gender, male or female, the age of the patient at the start of the study, patient height and weight, and then some other symptoms that might be related to the reason for their passing. So let's just read up a little bit more about the data set before we continue to understand the data a bit better. Okay, so here I've simply searched the SAS documentation, sashelp.heart, and this is the heart data set. We can see that this study is called the Framingham Heart Study, and the data set contains 5,209 observations. This study was done on heart diseases, and according to the literature, the study was a long-term cardiovascular cohort study of the residents from Framingham City. That's a city in the United States. And the reason that this study was done was to find out more about the epidemiology of hypertensive or arterial sclerotic cardiovascular disease. These are heart diseases, and the reason why the study investigated factors, as we see here, like cholesterol, smoking status, weight status, is because these are suspected comorbidities for the aforementioned heart diseases. And the study is quite old. It was done in 1948. So a lot of what is in this study we know now as common knowledge. But back then, they were still investigating the so-called unfamiliar diseases. Yeah, so that just shows you how much society actually developed in 70-odd years' time. Okay, so let's have a look at a few of these variables and try to plot them. And look at the proc means, the summary statistics for these variables. So let's draw up some basic summary stats. Just to recap, you go to Task and Utilities, and then under Tasks and Utilities, you scroll down to the Statistics tab. And you'll find Summary Statistics. Double click on that. And then we need to choose the data set, what we want to work with. Our data set is found in the SAS Help library, and it's this HEART data set. It's shown now as sashelp.heart. SAS Help is where the data is stored, and then the part that's after the dot is the actual data set name. Let's investigate the age at start variable and the cholesterol variable. If we navigate to options, we can include the skewness and kurtosis. And then click on Run. Looking at the code, we see it's the proc means procedure SAS Studio utilizes to give summary statistics of the data set HEART. We've chosen to include the mean or average, standard deviation, minimum, maximum, n, which is the number of observations, the skewness, and the kurtosis. The variables we are investigating is the age at start and cholesterol. So the age at start. What does that variable mean? According to what I could find, the age at start variable most likely explains the age at the time of the exam in years. And that generally ranges from 32 years to 81 years for the broader study. The cholesterol is the serum total cholesterol in milligrams per deciliter. Keep in mind that the data set we're now looking at might be a sample data set of the entirety of the aforementioned study's data gathered. So let's run this statement. Remember, it's less important right now for us to understand exactly what the variable specifically represents, so do not worry if the terminology is unfamiliar. We are focusing on the concepts of skewness and kurtosis and the distribution of the variables, so that's where I would like you to focus on. But it's always interesting for me to understand the explanation behind each variable, hence the research, and it is needed for us to understand if the values are possible or if it's incorrect measurements or not. So we note that the age at start is a mean of 44 years, standard deviation of 8, minimum age 28 in this data set, and the maximum is 62. There are 5,209 observations, so it seems like the cholesterol variable in comparison has some observations missing. The skewness is quite low for the age at the start variable, 0.19. And the kurtosis is negative 1.1 for the age at start variable. For the cholesterol variable, we have a mean of 227. Standard deviations 44, minimum of 96, maximum 568. So like we said, we have some observations missing in this variable. The skewness is not too high, it's not above 1, and the kurtosis is 2.1. So let's create a plot so that we can see how the variable's distribution looks with a superimposed normal density curve. Click on Run. we've added a normal density curve to the age at start variable and the cholesterol variable. Let's investigate the age at start variable. So, if you remember what we mentioned earlier in the lesson when we were being introduced to kurtosis, we mentioned that kurtosis is a dimensionless quantity. And the reference quantity that we use for kurtosis is that of the normal distributions, which has a kurtosis value of 0. Some researchers consider a kurtosis value of higher than 3 or lower than -3 to be excess kurtosis. So that means that it's outside the ranges of normal. And when we look at the systolic variable, we notice that the kurtosis is 4.228. So that is a little bit high, according to what some researchers recommend. And what I would recommend in a case like that is to also have a look at the shape of the distribution. So you will find that if the data has a negative distribution, like with the age at start variable, the distribution will tend to be flatter and broader. And sometimes the tails will be thinner than that of the normal distributions. So we've superimposed the normal density curve over the age at start histogram plot. And you can see that it does appear as if the distribution of the age at start variable is broader and flatter. Almost uniform, which is strange, but we will address that in a bit. This variable has a distribution with a kurtosis of -1, therefore not, as suggested by some researchers, that much deviated from normal. But when we look at the variable systolic, that has a kurtosis that's higher than 3. We expect, according to the literature, that the peak is more narrower than that of the normal distributions, and the tails will be thicker or fatter. And if we compare the histogram of the systolic variable to the superimposed normal density curve, we do indeed find that the peak is higher than the normal density curve, and that the right tail is indeed fatter than that of the normal density curve. Then furthermore, what the literature also tells us is if the kurtosis is negative, we can expect there will be fewer outliers or less outliers. So less outliers will be further removed from the middle point or the center of the distribution. So in other words, we will expect that the observations will lie closer to the center of the distribution. And in contrast, if the kurtosis is positive, we expect that the outliers will be further removed from the center of the data. This is indeed the case when we investigate the histogram or the plot of the systolic variable. There are more observations that are further removed in distance from the center of the distribution in comparison to the age at start variable, where there are less variables that are further removed from the center of the distribution. What I would like to recommend, or would like you to remember, when you search for kurtosis, it will often be referred to as the peakedness of the data or the distribution. But when considering kurtosis, we should in actual fact not focus on the peakedness of the distribution, but more on the tails of the distribution. We should rather investigate the thickness of the tails and not how peaked the distribution is. And then just something interesting to note about the age at start variable is that the minimum value is 28 and the maximum value is 62. But considering these values logically in a real life scenario, we do find patients that are older than 62 with these specific heart conditions. So it appears as if this particular study sample of the data set had decided to cut off the minimum and the maximum age. And that is also a likely reason why the distribution of the age at start variable is shaped almost uniformly, because our interval for this variable is bounded. And this could also be the reason it appears as if there are little tails as a part of this variable. But in actuality, it could be because the study itself did not accept participants below or above this age. And then to conclude this demonstration, I want us to think a little bit more about the interpretation of kurtosis. Kurtosis is not necessarily a mathematical rule as to show the difference in fit from a normal kurtosis or what is an out-of-bound kurtosis for a specific distribution. It's more of an intuitive concept, so there are many articles that speak to the relationship between kurtosis and the shape of the distribution. An article that SAS recommends or that SAS finds to be a good explanation is that of Berlinda and McGillivray that was published in 1988. In this study, the authors provide 3 examples of the different densities where kurtosis is the same. The kurtosis value is the same, but the distributions look very different to each other. These authors recommend that kurtosis should rather be defined in terms of, and I quote, the location and as a scale-free movement of probability mass from the shoulders of a distribution into its center and tails. In particular, this definition implies that peakedness and the tail weight are best viewed as components of kurtosis. This definition is necessarily vague because the movement can be formalized in many ways. So what I took from this article was that in order to know if the kurtosis is high or low for a specific distribution, we have to gain more experience on working with the particular concepts of kurtosis and skewness, because these concepts might look very different depending on what industry's data we're working with, or as we've seen earlier, if the variable is bounded or not. Therefore, there are a lot of different factors that we have to take into account. And it's not as simple as just saying that if the value is higher than 3 or lower than -3, it's high or low, although that is a good place to start. I will also include some of the articles that I found in the summary notes, as always, so that you can go and research the concept of kurtosis and skewness further on your own and come to understand the concepts better, as it's not possible for me to supply you with each and every one of these articles' ideas during the short time that we have available during the lesson. Wow, what a mouthful. Let's stop and stretch a bit and give our brains some time to digest all the information it has consumed before we dive into the next topic of the day. Let's all take a few seconds to step away from the desk, stretch, and breathe. Congratulations, you've made it all the way to topic 2 of this lesson. Let's investigate more distributions apart from the normal and Bernoulli we've already introduced. So how did probability distributions come about, and whomever came up with the concepts of them? Although the concept of probability theory might have originated much earlier on, it is said that the idea came about with a game of chance, when the famous Girolamo Cardano, physician, mathematician, and gambler, wrote a short manual in the 15th century called Games of Chance. He introduced the idea of what we know as probability theory today. Cardano's ideas were elaborated on during the 16th and 17th century through games of chance, like throwing dice and tossing coins. And in 1654, Pascal and Fermat, through enthusiastic correspondence, formally introduced the concept of probability and is what we consider as the emergence of classical probability theory. In the previous lesson, we got better acquainted with Bernoulli distributions. To recap, the Bernoulli distributions is a discrete distribution that can take on outcome values of 1 or 0. The Bernoulli can be seen as a special case of the binomial distribution. The Bernoulli distribution conveys the results of a single trial, whereby the binomial distribution conveys the results of n trials. As we've just mentioned, the binomial is closely related to the Bernoulli distribution. Where the Bernoulli distribution is the result of a single event, the binomial distribution is the result of an experiment being repeated many times over. Each outcome being independent from each other, of course. The binomial distribution, like the Bernoulli, has the outcome of success or failure with each experiment conducted. So let's have a look at an example to gain a better understanding of the binomial distribution. If we once again take the experiment of a fair coin flip, but instead of flipping the coin once, we now flip the coin twice. We know that the coin can land on either heads or tails. As we noted with a single coin flip, the chance of success for each trial is 0,5, and the chance of failure is 0,5. The chance of the coin landing on heads for both of these trials are 0,5 times 0,5, which is equal to 0,25. Remember, each coin flip is an independent event, meaning that the events do not affect each other. Therefore, if we define the coin landing on heads as a success, we note that the probability of the coin landing on heads once is the highest. The next distribution we will familiarize ourselves with is the Poisson distribution. Similarly to the binomial, the Poisson is a discrete distribution. Therefore, it can only take on certain values. The Poisson distribution is used when to ascertain the probability of a rare event occurring. For example, to calculate the number of instances taking place in a specific time frame, given the number of times the event occurs over that period. Let's have a look at a real-life scenario where the Poisson distribution is handy to aid our understanding of this distribution. So let's imagine we are the owners of a pizza restaurant. On average, we have 3 pizza orders per minute. This number, however, is merely an average per minute and can vary widely based on the time of day. We could use the Poisson distribution to calculate the probability of numerous events regarding how many customers will order pizza. The Poisson distribution aids us in calculating more precisely how many pizza orders we will get during more and less busy periods. With this information, we're able to better understand and plan for peak and off-peak times. Remember, all the summary notes and slides are available in your toolkit and would really be worthwhile to keep as a resource at your fingertips beyond this course. But no sneak peeks. The lesson notes will only become available after you have attended your class or caught up with the lessons. These will also help you prepare for your assignments. In Lesson 7, you can expect to uncover the concepts of inferential statistics, statistical methods used to draw conclusions from the sample to make conclusions about the population. Prior lessons focused on descriptive statistics because they helped us to describe and summarize the data through various methods like plots and summary statistics. Lesson 7 will introduce concepts like estimation and hypothesis testing, from which we will be able to generalize information about the population from the sample. We are at the last topic of the day. Don't stop learning now, you're almost over the last hurdle for today. We will now tackle the concept of sampling distributions that'll in turn enable us to understand estimation and hypothesis testing that we will deal with in the next lesson. The distributions we've learned about thus far helped us determine the probability that a specific measurement forms a part of the population. Sampling distribution is the statistic that we've gathered from a larger number of samples that we've drawn from a certain population. The sampling distribution provides us with the occurrence of a scope or range of possible outcomes that can occur for the given statistic of the population. As mentioned, knowledge about the sampling distribution will enable us to utilize tools like hypothesis testing and estimation. We make the assumption that a sampling method like randomized sampling was used to gather the sample data. If proper sampling techniques were not used, the sample will be biased, and we will not be able to utilize tools like estimation with trustworthy results. Before we go any further, let's recap what a population and sample is. A population is in reference to a whole group. This can include an entire group of people, or objects, or events, or measures. We therefore refer to a population as the entire group from which we want to make assumptions. The sample refers to a subset of the population. The sample will therefore always be smaller than the population. The sample is a smaller part of the whole of the population. 4 features explain a sampling distribution: statistic of interest, random selection of sample, size of the random sample, and specification of population being sampled. The statistic of interest is, for example, the standard deviation or the mean. With the second feature, it's as simple as it's stated. The sample must be randomly selected, otherwise bias is introduced into the sample, and it will not be an accurate representation of the population. Thirdly, we always aim to include a sample that is big enough according to the central limit theorem. And we define a sampling distribution through the specification of the population being sampled, meaning that the population specifications will in part determine the specifications for the sample. Another topic that I would like us to recap today is our VIP friend, the central limit theorem. We've gained an understanding of the general concept of this theorem in previous lessons, but let's use this time to focus on the features of the theory. Firstly, according to the central limit theorem, if our sample size is big enough, the mean of the sampling distribution will be equal to the mean of the population based on the independent observations. Secondly, the standard error of the mean, calculated by dividing the standard deviation by the square root of the sample size, is equal to the standard deviation of the sampling distribution. And thirdly, from the central limit theorem, we can deduct that the population is normally distributed. Remember that we've previously stated that a sample size of 30 is our minimum sample size for it to be considered normally distributed, if the population is normally distributed. We will, however, continuously elaborate on this theorem as the lessons continue. The mathematical proof of this theory is like a work of art, and should you be interested in viewing it, you can find a link in the summary notes. The 5 practical skills that we will develop in the probability and statistical analysis course include fundamentals of stats, exploratory stats, inferential stats, statistical programming, and presentation of results. Congratulations on embarking on this journey, and have a look at the skills you've acquired so far. This is just the tip of the iceberg, as in stats, you never stop learning. We will continue to check in with you and your progress for the rest of the course. Keep it up. Why not think about what you want to do beyond this module or beyond this course even? At Shaw Academy, we offer different memberships that will fit your lifestyle and learning pathways to enable you to build your own skill set. Some knowledge about technology, coding, and Excel is paramount on the journey to becoming an analyst. And luckily for you, Shaw Academy can help you improve on each of these skills. It's time for your weekly assignment again. While these assignments are not for marks, they will definitely help you prepare for the final module assignment. For this week's challenge, I want you to practice the concept of binomial distributions with an old-fashioned fill-in-the-blanks exercise. You can find the template for this exercise under the bonus content. With only 2 lessons to go until the end of this module, I'm sure you are just as excited as I am. See you soon for Lesson 7.